talk. Professor Sterling, as many of you may know, is a forerunner in the cluster computing. He's one of the first who managed to cluster community computers to make an HPC computer. Professor is currently in Indiana University. I make it short, Professor, so you may start this. We have 25 minutes for your talk, perhaps 5 minutes for a couple of questions today.
Thank you very much. So I'm considered one of the experts in the field of computers, and I don't know how to use a Microsoft Windows PC. So you're watching me do a wonderful thing, or not. Excellent. Thank you very much. Well, first, I cannot adequately convey to you how pleased I am to be here. I am truly honored by the opportunity to come to your beautiful country and to speak to this audience. I can only allude to Dr. Meritari, forgive the mispronunciation, and of course our friend and colleague of many years, Lucio Grandinetti. I feel like a new kid in a candy store. I look forward to talking with many of you over the next few days, and I look forward not to teach, but to learn from all of you about the society here and about the technical work being done. Please do not hesitate to come forward and ask me questions. I wish for that opportunity to speak to you. Now, our chair has said I have 25 minutes, so we will ignore that because I have like 25 slides, and I will talk to them as quickly as I can, but I want to convey to all of you a certain excitement that that my colleague Vladimir Voivodin and others have for the changes taking place. I enjoyed very much Professor Grandinati's comments. He managed to capture and span the total scope of the field of computing from its earliest nuances to the far future. It was a brilliant presentation. Thank you, Professor Grandinati. All right. So let's start with a motivating problem, a problem bigger than all of us. This is a picture, a diagram of two black holes. As many of you know, a black hole, at least according to Einstein equations, is a gravitational singularity that in its ultimate manifestation makes no sense and yet exists. And this is the case of an event that took place over 1 billion years ago with two black holes, each roughly about 30 solar masses, entering into a death spiral that culminated in a collision and an explosion of extraordinary power. On your right, you're looking at reality shaking. The collision of these two black holes created a single black hole, but 3 solar masses less than the two constituent original black holes. What happened to that mass? It was converted, all of it, to energy. In fact, in the few tens of milliseconds in which this event occurred, the power of this collision exceeded by almost 100 times all of the power of all of the visible universe combined. This is unbelievable. And furthermore, most of that energy was released as gravitational waves. It is a remarkable accomplishment of world science that we all share, that a year and a half ago, we were able to actually detect these very gravitational waves. In this case, it was done by the LIGO experiment. LIGO stands for Laser Interferometric Gravitational Observatory. In my country, it is funded by the National Science Foundation. It is the single largest experiment funded by the NSF. And after 10 years of operation, it saw nothing, zero. And yet, the foundations of theory dictate the existence of gravitational waves, or we don't understand science. And so this experiment was upgraded and continued, and when put back online, almost immediately, it discovered this collision of two black holes from its signature in gravitational waves. Now, these two interferometers, one is in the state of Washington near the West Coast, and one is in the state of Louisiana on the Gulf Coast. I spent several years teaching not far from the second interferometer. And these together both have to detect a gravitational wave for it to be recognized as an external event, rather than somebody stamping their foot 20 miles away. But it's more than just two very large, very sensitive interferometers that make this experiment successful. And by the way, the legs of those interferometers were more than 1 kilometer long each. The missing piece? High-performance computing. High-performance computers were required to measure the signals and extract the signal from the background noise, of which there was much. It had to be so precise that it could detect across more than 1 kilometer's distance a perturbation of space-time less than the width of a nucleus of an atom. This is maybe 1/100th or 1,000th of an angstrom, 10 to the minus 10 meters. Now, not only are high-performance computers required to measure the signals actually coming out of the interferometers, but those signals would have no meaning whatsoever, and therefore, in fact, not be detectable if the computers hadn't also simulated all of the phenomenology that was expected to generate these. Yes, like colliding black holes, or colliding neutron stars, or supernovae. All these many different forms of cosmological events have to be first simulated across their many parameters in order to identify the signature. And you see the signature here, this what is known as the chirp signal of the phenomena, in this case, colliding black holes. Here is a simulation, if I can show it. All right. There it is. Okay. I told you I couldn't use Windows. All right, yes. These are two black holes simulated using adaptive mesh refinement, actually, yes, that's right, adaptive mesh refinement, using the full set of Einsteinian equations coupled with hydrographical computations to demonstrate, and that went blank because the black holes went blank in that phenomena. Now, I'm going to describe a new class of computation, sometimes referred to as asynchronous multitasking, other times referred to as dynamic adaptive computing using runtime systems. This simulation that I just showed was conducted using these advanced techniques, as I will describe. But first, and perhaps I need not explain this to this audience, but for the purposes of justifying the following presentation, I would like to at least remind us of key fundamental factors. A simple but important and revealing performance model. The performance model on your left, which I guess would be over there, shows the average performance as a factor of 4 key parameters. Those key parameters are efficiency, scalability, availability, and then some unifying or utilization function. Let me put those in more realistic terms. The efficiency is the basic effect of the capability of the peak machine in the sustained performance. The scalability is the amount of parallelism that we can exploit, both physically and algorithmically. The availability is, well, the realistic percentage of time that the actual computer can be used for user science applications, not for maintenance, not for errors, broken, for the necessary work for a checkpoint and restart. And finally, this utility function is to first order representative of the speed of the logic, the clock rate, if you will. Now, each of these parameters are, in a sense, complex functions of 4 key factors. I represent this in the acronym SLOW, but colleagues of mine said, no, that's not good enough. You should actually make it slower to capture, in addition to the performance factors, the additional factors of energy and reliability. So it is slower for purposes of acronym. Starvation is the insufficiency or the inadequacy of the amount of parallelism or parallel work that is available to the computer, either because the work is not evenly distributed across the system, so parts of the system sometimes don't have work to do, or there simply isn't enough parallelism. Latency is the time distance of making an access to remote data or requesting a remote service call. It's the time back and forth. Overhead is that work we're forced to do to manage the parallelism, to manage the parallel tasks of the application, and to manage the parallel physical resources of the computer itself. And finally, contention. For the purposes of the acronym, we had to say waiting for contention resolution. That was a bit of a stretch. But the contention, of course, is the time or the delay time for conflicts of access to shared resources, either shared physical resources like the network, and this is measured by bandwidth, or say access to memory banks, such as bank conflicts, or to logical objects such as a synchronization variable, or some other global value. When you combine all these together, we have the guidance necessary to understand every high-performance computer ever built. Did that mean something I should know about? Here's an example of overhead. Now, it's normalized, it's analysis done, and it's normalized so much that actually the numbers don't have any meaning whatsoever. But the trend should be clear. In a fixed workload, the overhead work puts in a lower bound on the granularity, the size of tasks that can be performed. And for a fixed workload, that ultimately bounds the scalability. You see the flatlining occurring, the scalability, and therefore ultimately the performance independent of the amount of hardware that you throw at it. And there's an additional problem that we face at an increasing level, and that is asynchrony. Asynchrony is not merely the distance of latencies that we experience. It's not even, although it's part of, the variability of those latencies from near to far. It is, in fact, the uncertainty of those latencies, because the very same action performed twice can take different amounts of time. In order to address all of these problems, an alternative to the MPI, or even the combination of MPI and OpenMP, the communicating sequential processes model, first proposed by Anthony Hoare in the late 1970s, and that we've been using very successfully for 30 years or so. You might refer to it as the message passing model, a variation of which is the bulk synchronous parallel model that Leslie Valiant had proposed, that many of us use for the sake of simplicity. But these static methods fail to take advantage of runtime information, and as a result, only the information they have at compile time and at programming time can be exploited to determine the scheduling, the resource management of the system. I use a metaphor in these diagrams of a cannon. This cannon is actually in Moscow, someplace. The diameter of the mouth of the cannon is 1 meter wide. Now, why I bother to mention this is I can't help but note amusingly that the cannonballs themselves you see at the foot are actually greater than 1 meter wide. Needless to say, this cannon was actually never fired in the heat of battle. The other picture is one of a guided missile. So the cannon represents what you might call ballistic computing. You compile it, you program it, you load it, and you start it. And that's all the control you have over it. Versus what could be called guided computing, in which throughout the computation, runtime information is used to adjust and adopt using mechanisms for introspection to improve the behavior and the performance as the program evolves and based on the state of the machine itself. The communicating sequential processes model, or CSP, is an execution model. It's one of about half a dozen that were used throughout the 70-year history, and I'm about that old, 70-year history of high-performance computing, from the days of the vacuum tube and core memory machines up to the very largest, the Chinese machine, Taihu-Light, with 10 million cores and over 100 petaflops of peak performance. the vector model, the SIMD model, the venerable von Neumann model, as well as CSP, all represent transitions or paradigm shifts in the way we do computation. To do dynamic, adaptive runtime computation requires a new execution model. And I offer an example of such a model. We call it Parallax, that provides the formalism in which to build dynamic adaptive computers. Here's a diagram, really more of a cartoon, but it serves a purpose, of some of the key ideas. Now, our work borrows from these ideas, but I can assure you, many of the core ideas are found in prior art, some of them going back as much as 30 years, like the data flow model and the systolic array. Other pieces of work, other runtime systems being developed in Europe, in the US, and in Japan that I know of, and I'm sure there are others that I don't know of, perhaps here in Iran. Different runtime systems are also using different mixes, different collections in different ways of these same ideas. What are those ideas? Well, threads. Now, a thread is a piece of work that's performed in roughly a single location. That could be a single core, or in fact it could be a node of multiple cores. Within Parallax, we in fact don't use threads per se, we use more complex computations, much like data flow, where there's fine-grained parallelism even within the thread. The second idea is message-driven computation. Those of you who are students of parallel processing may be familiar with the work of Berkeley, UC Berkeley, on active messages. This is good work. But the notion of message-driven computation, again, goes back another 20 years before that, again, to things like data flow and the actors model. This is where you move work to the data rather than always gathering the data and bringing it to the work. The third mechanism is the notion of specialized synchronization objects. Again, prior art of data flow. This is the third or fourth time I've mentioned data flow. And from the actors model, the use of the futures construct. These together make up a dynamic adaptive execution model. They are placed all within a global namespace, address space, as opposed to the distributed memory systems, much of which we use today. There are many other elements of this, and I'd be glad to share with any of you a recent report of my colleague Jeremy Seek and his postdoc Mateusz Cimini in developing a formal specification using operational semantics of the Parallax model. Another colleague, Maciek Brodowicz, with my graduate student, doctoral student Daniel Kogler, has developed an event-driven simulator, similar to but more advanced than a queuing model simulator of this Parallax model. And we have done a number of quantitative parameter sweeps. This takes a look at one of the factors I mentioned, overhead, and another factor I mentioned, parallelism, this in the sense of number of cores per node. And statistically, modeling this space of behavior, and you see a very dramatic image. Within a certain scope of the range of these just two parameters, you see a plateau, little difference. That's where you want the computer to constantly adjust itself to operate at. But if it doesn't, and if either of those parameters go too far in their respective dimensions, there are steep cliffs in which the performance drops dramatically. And it is that plateau that one wants to use your computer's in. And so we develop runtime systems, software that helps match the needs of the application computation with the resources of the parallel computer. Here's oh, thank you so very much. Yes, slowly my voice is degrading. That's good. Now I'll probably drop it somehow. Let's see. All right. Here's the block diagram of the runtime system, and you'll observe that each of the major actions I described a few minutes ago in Parallax are represented by pieces of the runtime system. We call the runtime system HPX, and there are several code bases that represent that. And this is built, of course, on top of the hardware computation and network, and also the operating system. Here is a second. Okay, we play this game. Come out, little mouse. There it is. All right, now this is a wavelets computation, also dynamic and adaptive. This is an exploding star. And there are two shock waves, the outer shock wave and then the inner shock wave, which is actually faster and is combining to create the turbulence you see in light blue. Now this curvature you see, this perfectly spherical structure, this isn't built into the code. This is an emerging property or behavior of the computation itself. And this was done using HPX for far greater efficiency. Now, for purposes of integrity and honesty, we're all scientists, right? And negative results are not failures. Positive results are not the only measure of success. In fact, we learn more from negative results than we do from positive results. Positive results merely confirm our expectations. Negative results tell us, inform us that there's something wrong with our ideas. And so we thought, of course, that we were developing the final solution, the end result. Everybody would use it. It's not true. There are many applications for which, frankly, our runtime system approach is not sufficient. Here's an example, a code called Lulish, used extensively by our Department of Energy. If you look on your left, you will see an MPI version and an HPX version of the Lulish code. And over a couple of hundred cores, they're roughly the same. HPX beats MPI in a few places, MPI beats HPX in a few places. But when we run these problems going out tens of thousands of cores, here it's between, it's supposed to be between 30 and 40,000 cores. You can see, in fact, that the MPI code does about 40% better. And this isn't just an happenstance. This is the result of a failure due to the overheads and other factors imposed by the runtime system, in addition to the regular work. So not all problems that are perfectly regular and perfectly static do not benefit from runtime systems. However, here's a case of a sparse matrix vector multiply. You will have seen the kernel of this code in the HPCG benchmark, which has been developed by Jack Dungara and his team. And here you find in the bottom two codes, an MPI code and a HPX code, in each case with one thread per core. And as you can see, their performance is almost identical. But what HPX does is it allows what some people would refer to as over-decomposition. More parallelism than there are cores. And here you see a significant difference. MPI, the red line, cannot take significant advantage, although much better than single threads. The Parallax HPX green line clearly takes much greater advantage of the existing resources. But again, There are problems with today runtime systems. First, they're experimental, so they're not quite as reliable or firm. Secondly, they impose additional challenges in how to use them. They add overheads, which I know is counterintuitive for the purposes of speeding up a computation. The programming interfaces are non-standard and in some cases, like my own, not very good. How we support legacy codes is yet another challenge, though that's been worked by such people as those at Rice University. And then there's the notion of interoperability with libraries that have been developed over the decades. I've mentioned overhead before. Here is a surprise. We measured the overhead very carefully. Again, this is the work principally by my graduate student, Daniel Kogler. We wanted to know how much time different overheads took. If that is what we saw, we'd have a single green bar for each of these different examples. Let's just look at the middle of them. This is context switching. You don't see a single bar. You see, in fact, a variation of about a factor of 2 in this case. We did not expect that. We have analyzed the sources of this, and what we have found is increasing factors that create uncertainty, to which the runtime system has to adapt. This is another challenge. So we're very excited about the possibilities we see, the advantages that we can gain in scaling and efficiency. But there is much work to be done. I close with this slide. When we look forward, as Lucio suggested, we will look towards possible revolutions, not simply incremental extensions to otherwise conventional practices. With the end of Moore's Law, with the end of Dennard scaling, we are flatlining the standard techniques that we've been using, the exponential growth that technology advances alone have provided with the help of architecture. In the long term, yes, there are possibilities of quantum computing. But there's another possibility that is not being looked at, and that is still using the enabling technologies, CMOS and other semiconductors, but changing the architecture. Even today, the architectures we use commercially, while varying from past architectures, are nonetheless derivatives of the original von Neumann architecture. We're still doing sequential instruction issue. We are still trying to optimize for the floating point unit. Let me be frank, that's crazy. When I was as young as some of the students I see, that was the right thing to do. They were expensive. They were big. Today, they are inexpensive. They are small. Yet the entire rest of a core architecture, including the caches and the speculative execution and the branch prediction, and a bunch of other things, they're all there for no other purpose than to make that tiny little FPU run efficiently with high utilization. It's not only crazy, it's stupid. And finally, is the continued separation of the processor cores and the memory banks. We even call that the von Neumann bottleneck. Yet we keep them separate. So my final point, my final comment is a future, a revolutionary future, still using technologies that exist and exploiting the multi-billion-dollar fab lines, should nonetheless be building architectures with very different characteristics. Floating point units should be there in abundance, permeating the entire logical system and memory system. for high availability and low latency, not for high utilization. The hardware should include mechanisms to support the global parallel computation, not merely the sequential execution that goes back as much as 70 years. And we should take the memory and the logic and merge them together and add to that nearest neighbor communication for one single combined logic element, a new component, a new device from which we can build the future exascale and zetascale computers that will drive us through the end of the next decade and not just the end of this decade. Thank you all very much for your attention, your time, and I hope you have found this as interesting as we find the work that it represents going into the next research paths in high-performance computing. Thank you very much.
Can you take questions?
Of course.
Can you have just short questions, please? Very short time. Any questions? Yes, please.
Professor, I believe one thing that perhaps, I'm not sure if I have missed it in your presentation, I'm not sure, is that the programming paradigm is something important that is still lagging behind. Very, very, very important factor. Legacy codes suffer from our conventional programming models. And what are we going to do about it?
Well, first, you're absolutely right. Indeed, sometimes you would just throw up your hands and give up because of the programming, the parallel programming models. Much of the parallelism I have described that is available today is not exploited because the user interface, the application programming interface, is not sufficient to expose within the application all those different forms that could be exploited by the runtime and the architecture systems. What are we going to do? Anything I would say would have many people who disagree with me. If I were to say, obviously, we need a new programming language, some of the brightest and the best-known people in our community would immediately disagree, say this is absolutely counterproductive, like MPI, like OpenMP. What's interesting, however, is people say we can't have new languages, on the one hand, we have to have the same thing, and on the other hand, they still add new things, like CUDA, or OpenACC, or OpenCL. So there's this contradiction in our community that they don't admit to. But it is absolutely true that across the world, and I'm sure here in Iran, there are many Fortran codes and MPI codes in the aggregate worth tens of or hundreds of billions of euros or some other currency of your choice. And we have to find ways to bridge the gap between those old techniques of limited parallelism and the new techniques of greater parallelism. How are we going to do that? Ultimately, individuals, in spite of collegial contradiction, will make the steps necessary to provide new ideas. And when they work, people will get on board. I don't have the absolute answer. My programming interface is poor for that purpose. It's fine for my purpose, which is to experiment with new system designs, but it's lousy for doing new applications. Is there another question?
I have a related question. If people start investing in rewriting code, do you see new programming models that would be more portable so that they don't need to be re-implemented again?
That's, again, an excellent question. Many people, many of our best programmers, our computational scientists, say, I'm willing to rewrite my codes, but only once. And it's for this reason. The two objectives that we need, and they're interrelated, are user productivity and performance portability across systems of different types, systems of different scales, and systems of different generations. And the notion of a runtime system is an amplifying effect on the user productivity, because it serves, many of you may be familiar with virtual machines, and it serves as a kind of virtual machine, but for high-performance computing, in which as the machines change and the applications change, it adapts to those changes, not requiring greater effort or burden on the future computations. So your question defines a requirement of future programming models and runtime systems.
Thanks very much, Thomas.
Thank you all very much again for this opportunity, and I'm really looking forward to the rest of this conference. Thank you.
May I invite Professor